Hello, Chemistry of Earth and Space Science. We are in Unit 4. This is lesson number 3, all about exothermic and endothermic reactions. Our objectives for this PowerPoint, and the objectives are probably longer than the PowerPoint actually, is to first be able to distinguish between a system and surroundings. Second, to be able to use interaction of energy between the system and surroundings to determine whether or not the reaction is exothermic or endothermic. We want to be able to interpret potential energy diagrams. Another name for those are enthalpy diagrams. We want to determine if a reaction is exothermic or endothermic from the diagram. And in looking at the diagram or the graph, we want to determine the potential energy of the reactants, the potential energy of the products, the heat of the reaction, the potential energy of the activated complex, and the activation energy itself. And then finally, have an idea what happens to a reaction when we add a catalyst. So the administrative pieces, there's 2 handouts that go along with this session, exo and endo classwork, and then there's also one on interpreting enthalpy diagrams. So just in general, if you hear the terms exo and endo, what do they mean? The place that most people recognize it is the skeletons. There are exoskeletons and there are endoskeletons. We as humans have endoskeletons, meaning the skeletal structure is on the inside. Things like crabs and shellfish and shrimp, they have exoskeletons, those where the skeletal structure is on the outside. So what do you think would be meant by the terms exothermic and endothermic? So what's the difference? So when identifying whether something is going to be exothermic or endothermic, we need to look at the system and the surroundings. We need to figure out which direction the energy of the reaction is going to go. I said in talking about balancing chemical equations that all reactions will have some sort of an energy change, whether the energy be released or energy be absorbed. When looking at the difference between system and surroundings, the system is the part that you're going to study. And for us in a chemical classroom, that's usually the chemical reaction. And the surroundings are the rest of the area. And sometimes that's just how it feels, what it does to the surroundings. Does it feel warm? Does it feel cold when touching the reaction? And then in endothermic reactions, we study the interaction between the direction the heat transfers between one to the other. So here's 1 or 2 examples. Here's an egg dropped onto a hot summer day sidewalk, and the egg has fried. So the system and the surroundings, well, in this situation, the system would be the egg. The egg is our system. We want to determine what happens to the egg. And we know that the surroundings, the concrete, has put energy into the egg to make it cook. So the system would be the egg and the sidewalk would be the surroundings. Another example, again, stolen from Science Source. Identify the system's surroundings of, say you have a piece of ice in your hand. It's melting. So if we focus on the ice cube itself, the ice cube itself is absorbing energy from our hand and also from the air. So the system would be the ice cube and the surroundings would be the hand or the air around it. So if a reaction is going to be exothermic, that means it's going to release energy, is going to exit the system, that energy is going to leave the system, which means we normally feel exterior feels hot. Usually what happens is the system has a lot of energy or temperature and it pushes it into the surroundings. On a chemical reaction, the chemicals themselves will be storing energy and they're going to release that energy into the surroundings, so it'll feel hot. So this picture up in the corner, around the reaction you would probably feel warmer. The energy is being removed from the system and going into the surroundings, and that's what's making the reaction take place. Some examples. Here's one of these hot hand warmers. This is a good example of an exothermic reaction. In this situation, what is the system? So it depends on really what we're studying, but let's say the system is the hand warmer itself and whatever chemicals are in there. Truth be known, hand warmers are kind of simple. They're just magnesium and some salt, and they react with the oxygen in the air. Okay, so we have that hand warmer is going to be our system. What's the surroundings? Well, in this case, the system is going to release energy and it's going to go into our hands, or maybe the fabric around our hands, maybe the glove, whatever. All those things are going to absorb some of that heat. And then why is it exothermic? It's because the heat from the reaction goes outside of the reaction, leaves the reaction, and makes the surroundings increase temperature. Other examples, common examples, are freezing an ice cube, water condensation, hand warmers, I already said, and combining chemicals in a beaker or a Erlenmeyer, and the beaker feels warm. That means the reaction generated heat. That's exothermic. Endothermic is the opposite. Endothermic is when the system absorbs heat from the surroundings. So both of our earlier examples, the egg and the ice cube, both were endothermic reactions, according to the egg or the ice cube being the system. The system's usually at a lower temperature, and it absorbs some energy from the outside to bring its temperature up or to produce some sort of a event. That's embarrassing. Okay, sorry. So what happens is the surroundings will usually, not always, but usually will feel cooler. The reaction is going to absorb some heat, and that's what makes the reaction take place. So here's an example of the ice pack. So this is called hot and cold packs, is the unit, all about reactions, and this is where the hot and cold packs are. The hot pack was the hand warmer. It released heat into the surroundings. This would be ice pack. If you've ever had an injury, they put a bag of ice on it, or maybe put one of these compresses on it, and when it does, the ice pack makes your foot feel cool. So what's the system? Well, since there's a chemical reaction going on in the bag, we're going to say it's the cold pack itself is the system. So it's absorbing heat. Where is it absorbing heat from? Well, it's absorbing heat from the air, but also from your ankle. This is the whole point of the cold pack, to pull that heated energy, that energy is generated because of an injury, away from the injury. So it's endothermic because the heat in the cold pack is absorbing energy from the surroundings, the ankle and the air, so the energy is being absorbed by the cold pack. Here's some other examples: melting, cooking, water evaporation, and then put substances together in a beaker and maybe they feel cold. So what happens during a chemical change? So whenever a reaction takes place, we know that we're going to have new materials being formed. And the tricky part here is that whenever we have a reaction take place, whenever we have a reaction take place, if we break bonds, which we're going to have to do, and when we break those bonds, one of the things that's going to happen is I have to put energy into the system. Now, I think about this like there's an old game, very old, way probably older than any of you guys are, of Red Rover, send so-and-so over. You probably can't do that anymore because, people don't like slamming into other people. But the kids would all hold hands, and you'd claim, hey, Red Rover, send Chris over. And Chris would come barreling towards the hands, trying to rush as hard as he could in order to break the connection. Well, obviously, in order to break that bond, break that connection, you have to put energy into the bond to break it. So that's why breaking bonds require energy to be input. That means because making bonds is the opposite of breaking bonds, that means that making bonds is going to release energy. So it's going to be exothermic. And what happens to determine whether or not a reaction is going to be exothermic or endothermic total is you would take the sum of heat lost versus heat gained. And depending on what is higher, if it loses more heat than it gains, if it takes releases more energy in making bonds than it does in breaking bonds, it's going to be an exothermic reaction. However, the reverse is true. If the breaking of the bonds requires more energy than the making of the bonds releases, that means it would absorb some of that energy and it would become a endothermic reaction. So it's all about making and breaking bonds. Every chemical reaction has a situation where you're making and breaking bonds. Those making and breaking bonds on a submolecular level, intramolecular level, dictate whether or not the reaction is going to be exothermic or endothermic. Another way to diagram or show reactions is like this. These are both very, very primitive. We're going to make it a little fancier in a second. Energy diagrams. You notice on the left-hand side, on the y-axis, we have energy. That is actually the energy stored by the compounds. So you can see on the exothermic one, the reactants have more energy than the products, meaning that the reactants lost energy. It went from a high amount to a low amount. That is going to be an exothermic reaction. The opposite is true. If as the reaction takes place, the reactants become products and the reactants have less energy than the products, that means when we're done, we have absorbed energy from the surroundings. That means this reaction is going to be endothermic. These are very primitive, missing some key pieces of what are called potential energy diagrams or enthalpy diagrams. So here's what one looks like. So this is a potential energy diagram. They always have on the y-axis, it will almost always have a, I'm going to pick a different color. We'll almost always have a indicator as to what that is. This one says potential energy, and it's going to be listed in kilojoules. And across the bottom, the x-axis, it proceeds from beginning to end. So this is a reaction that, let's see if I find my cursor, that A, B are reacting to make C and D. That's my chemical reaction. A and B are my reactants, and C and D are my products. So if I want to know the potential energy of the reactants, I'd look at my graph, and I'd say, look, right here, that is 40 kilojoules. That means that my potential energy of my reactants is 40 kilojoules. Potential energy is the y-axis. From 0 up to my reactants is the amount of energy they have. Reverse over here, if I look at the products, the energy here, the difference here is 20 kilojoules. So my products have 20 kilojoules. So if I want to know what the heat of the reaction is, it's going to be products minus reactants. It's always products minus reactants. Products minus reactants. So that would be 20 kilojoules minus 40 kilojoules, or a negative 20 kilojoules. That means this reaction, this difference here, when going from reactants to products, this reaction lost 20 kilojoules of energy. That's not, it doesn't look like a J, it looks more like a T. There we go. So what's the activation energy? So right up here, this tippy top here, this is called the activated complex. The activated complex is this in-between entity that exists when the A and B collide together, and right before they decide how they're going to rearrange their atoms, they're all together. A and B, all the elements that are part of A and all the elements part of B are all together in one big blob. That blob is called the activated complex. So in this situation, this distance here from 0 up to the very, very tip top is the potential energy of the activated complex, which looks like this is going to be, so I can find my cursor, there he is, 100 kilojoules. I have to get this thing up to 100 kilojoules total potential energy before it can react and come down to a lower potential energy. How much energy do I have to put in? So if I think in terms of this hill, how much energy do I have to put in this hill to make the energy make it to the top? Well, if I've got 40 down here, and I got 100 up there, that means my activation energy is 100 minus 40, or 60 kilojoules of energy. That means this reaction will not take place unless I put into it 60 kilojoules of energy. All reactions require some activation energy, something to activate it, to get it started. Okay, let's look at the next side. This is my endothermic reaction. Notice that my energy is going from here to here. I hate my cursor. So in going from there to there, I have a certain amount of energy that is going to be lost, and it's going to go into this reaction. I'm just going to absorb energy. So if I look at my graph, right here I have the potential energy of the reactants. That's got a solid 50 to it. Products, that's over here. That's got 100. So 100 kilojoules of energy. Ooh, that's terrible. 100 kilojoules of energy. The heat of the reaction, well, that's going to be my 100 minus my 50, or it's going to be 50 kilojoules of energy is going to be absorbed this time because I'm getting a positive number. The reaction is going to change. It's going to have 50 kilojoules of energy go into the system. What's my activation energy? That's that distance that it takes to go up this hill. So if I take the top of the hill, which is 250, and subtract from it 50, I get that I need 200 kilojoules of energy to be put into the reaction before the reaction takes place. Up at the tippy top, this shows the activated complex, and that says the potential energy of the activated complex would be that 250. That one just looks terrible, so I'm going to get rid of it. See if yellow is better. Okay, get back over here. That means my activated complex is 250 kilojoules of energy. Okay, so we have these values we can read off of a potential energy diagram. It goes from left to right, just like our chemical reactions do when writing on paper. The left-hand plateau is my left-hand plateau is my products, is my reactants over here. Oops, and over here is the products. So what's up with that bump? That bump is how much energy I need to put in to make the reaction take place. Every chemical reaction has to have some energy put into it to get it started. Now, often that energy is absorbed from the surroundings. Okay, we have our situation where we have our surroundings, and it's going to absorb all this energy or release the energy. Lastly, what's a catalyst? So in chemical reactions, there's this thing called a catalyst, and you'll hear a lot more about catalysts in biology whenever you take that. But a catalyst is some compound you can add to a reaction to make it react faster. So for instance, in that hand warmer experiment, the hand warmer thing, what I said a hand warmer was simply a reaction of magnesium. Where's my cursor? There he is. Magnesium reacting with oxygen, and it's going to produce magnesium oxide. And I got to balance this because I have to. Okay. So magnesium is going to react with oxygen. It's going to make magnesium oxide, and that's going to be an exothermic reaction. But in order to speed it up so that you can really get full impact of the heat that comes from that reaction, it's going to add salt as a catalyst, something that's going to speed up the reaction without itself making the reaction go without being changed. It goes in salt, it comes out salt. It just speeds it up. So two conditions for a catalyst: speeds up the reaction and it can't change. Well, how does it do that? It does that by lowering the activation energy. If I look at these two examples, I've got the one path that's higher, that takes up much more energy, the uncatalyzed pathway. But if I add a catalyst, notice my reactants don't change. My products don't change. The change between the reactants and products don't change. But how quickly it gets there changes, and that's because we've reduced the energy, the activation energy for the reaction. And that's how that reaction, when we add sodium chloride to it, goes faster. It changes the activated complex. Now the activated complex includes the sodium chloride. So again, looking at this, I've got these reactions. I've got my different situations. I got in this guy here, I got my potential energy of the reactants. Let's see, that's going to be my 15 kilojoules. I think my videos would be half as long if I wouldn't have this cursor issue. My next video, I'm going to try to use a different tablet. Okay. Products. Well, that's all the way down here. That's not 50 kilojoules. What did I do there? Cross that out. Go away, bad. The reactants are this distance here, which is 65 kilojoules. I was reading the heat of the reaction. My products were 50 kilojoules. The heat of the reaction, that's the difference. That's my 15 kilojoules. My activated complex, well, that goes all the way up to here. That's going to be 90 kilojoules. And the activation energy is the distance between reactants and activated complex, and that is 25 kilojoules. So when the reaction goes faster, it does so by having the activation energy decrease. So if I do the same thing, same reaction, but now I'm going to look at the catalyst part. My reactants, let's see if we can do this better this time. My reactants were 65, that didn't change. My products is still 50, that doesn't change. My heat of the reaction is still 15, that doesn't change. But my activation energy now is only 10 kilojoules. I require less than half of the energy to be put in to make the reaction go faster, which means more collisions occur that work and a quicker reaction takes place. And in this case, our activated complex is only 75 kilojoules. That it is a different compound complex with the catalyst in it. That's why it can have a lower activation energy. So catalysts speed up the reaction, but also do not change the form itself. And that's it for lesson number 3. Come back in a little bit for lesson number 4. That's going to be one that starts the math up. Going to be all about significant figures and dimensional analysis. Expect that one to be a long series of videos. Have a great rest of your day. Toodles.